Elastic potential energy. A few centuries ago, Robert Hooke, a scientist from Britain, did some experiments to look at the relationship between the energy stored in elastic materials and the force used in order to stretch or compress those materials. And this has given us what we now refer to as Hooke's law. So if we stretch or compress an elastic material or device, like a spring or an elastic band, that stretch or compression is directly proportional to the force that's applied to the material. And that's really what Hooke discovered. So here we can see a string being stretched, unstretched on the left, and then stretched by different amounts in the subsequent pictures. The stretch or the compression is also referred to as the deformation. Here's the equation that Hooke discovered, showing us that the deformation, x, which could be the stretch or the compression, is directly proportional to the force exerted on the spring in this case. So there's the force exerted on the spring. Where x equals 0, the deformation is 0. That's called the equilibrium position. Conversely, the force that the elastic object or device exerts on the object, stretching it or compressing it, is equal to kx. So that, you might recall, is something we get from Newton's third law. If I pull on the spring to stretch it, the spring pulls back on me with the same magnitude of force, but in the opposite direction. So that's the indicator of the opposite direction, the negative. We can describe how difficult or easy it is to compress or stretch an elastic material using the spring constant, also sometimes called the force constant, for that object or material. We use K to represent the spring constant or the force constant, and K has units of newtons per meter. We can find this force constant by calculating the slope of a force versus extension or force versus compression graph. We could also call it a force versus deformation graph. So the slope here, rise over run, gives us the force constant for that spring or material, whatever that might be. We can see here that the units for the force constant, newtons per meter, make sense because, of course, our force would typically be measured in newtons, and our deformation would typically be measured in meters. Here's an example. A student stretches a spring by 15 millimeters in the horizontal direction by applying a force of 0.18 newtons. Determine the force constant for the spring. Here are the given values, and our unknown in this case is K. So we'll select our equation, in this case the equation from Hooke's law, and then we'll rearrange it to get K by itself, since K is our unknown. When we substitute our values in, as Gus would do, we do our division and we get 12 newtons per meter. As you might have surmised, the force that's stretching or compressing a spring is doing work on the spring, and that increases the spring's elastic potential energy. So really, we're using the work energy theorem again. The work is done to increase the energy of the spring. Note that this force is not constant, but increases linearly from 0 up to some maximum value kx. We can see that here. Our graph shows us a linear relationship. So as we extend or stretch the spring more, the force increases. But the average force on the spring is 1/2 kx. So our average value for the force would be right in the middle, right there, 1/2 kx. So if I want to calculate the work done on the spring, I can take that average force and multiply by the deformation, so 1/2 times kx times x, and I get 1/2 kx squared. So this gives me an expression for the work that I've done in stretching the spring, and so that must also give me the expression for the elastic potential energy for the spring, or in other words, the energy that's stored in the spring once it's been stretched or compressed. Let's look at example 2. A student stretches a spring with a force constant of 12 newtons per meter, 15 millimeters horizontally. Determine the energy stored in the spring. So our given values, we have our k value, our force constant, and we have the deformation of 0.015 meters. You'll notice I've converted from millimeters to meters. And our unknown is here. Our kinetic energy, or rather, that should be elastic potential energy. We'll fix that one. Our elastic potential energy is our unknown. So E sub E. Now we'll select our equation, and we'll use these should all be E's, elastic potential energy. So E sub E is equal to 0.0014 joules. So there's our elastic potential energy for the spring in this case. If we talk about an ideal spring, then we're talking about a spring that obeys Hooke's law perfectly within what we call the limits of compression or limit of deformation or stretching. Beyond those limits, the spring may be permanently deformed, unable to return to its original rest length or equilibrium state. So if we get beyond that elastic limit, the shape of the graph may change. It will be non-linear at that point. If we were to continue until we've stretched that spring into a wire, just a straight wire, then at some point we might see the graph take off sharply in this direction, because as we increase the force dramatically, there would be very little stretching of that wire. And then eventually the wire would probably break. All right, now we're going to try an inquiry activity to see how this elastic force and elastic energy works up close.